So I will just kick us off really quick. Good morning, everybody. Good afternoon, good evening, depending on where you are joining us from. I am Gretchen Hahn. I am a graduate recruiting specialist here at the College of Engineering at Northeastern University. Thank you so much for joining us today for one of my favorite type of webinars that we get to put on, one of our departmental research webinars. We in admissions talk all the time that the most valuable recruiting we can do is showing off our faculty and all of the amazing research that they are doing for the university. We know that they are the heart of everything that we do. It is the reason that students come to study with us. And they're really just movers and shakers, really doing a lot in the world. And we're very lucky to have them at Northeastern. So this is part of our series where we highlight some of the research going on in all of our departments. You are here for electrical and computer engineering and some research that's going on there. And we have an excellent faculty member with us here today. A joy to work with, absolutely wonderful work going on, who's going to take you through the bulk of the webinar today. So with that being said, I would love to turn it over to Josep Jornet. Take it away.
Excellent. Thank you very much, Gretchen. And good morning, everyone, or good day. My name is Josep Jornet, and well, as you can see here, I wear many hats. First of all, and the reason why I'm here today, I'm a professor in electrical and computer engineering. I also happen to serve as the Associate Dean of Research for the whole College of Engineering. And why not? I'm also the Associate Director of the Institute for Intelligent Network Systems. And we'll be talking about this. First, let me set the stage a little bit and talk about, well, just a summary, right? If you're here, you already know what Northeastern is famous for, right? And what Northeastern is famous is for our experiential learning. So we are a university that I would say in US standards, we're old and established, right? I'm originally from Europe, so this would be, not at all, but that's okay. We're a leader in experience-driven learning. We have many campuses, mostly in the US, Canada, but also in the UK. And in all these campuses, we offer degrees across levels, undergraduate, graduate, professional training. And in all of these, or in most of these, we do a lot of research. Now, you saw that I said that I'm a professor in ECE, I'm an associate dean of the college, but I'm also part of an institute. And I always find it that people are a little confused about, okay, let me see, my slides are moving, fine. Okay. I always find it interesting that people are, it's hard to understand. So let me put it this way. Northeastern, as a university, has many colleges. And for example, today, we're talking about the College of Engineering. But we have other colleges like, the Curie College of Computer Science, the Business School, the College of Health Sciences, this and that. Within a college, we have departments. And for example, I'm speaking on behalf of the Electrical and Computer Engineering Department, but we have other departments, chemical and environmental, civil and environmental, chemical, we have bioengineering, we have mechanical and industrial engineering, and that's all good. Now, what are institutes? Well, think of institutes as group of faculty and students across departments, even across colleges, that they work towards the same theme, towards the same goal. I mentioned that I'm the Associate Director of the Institute for Intelligent Networked Systems, INSI, and that's what is it? Well, it's a coalition of faculty and students primarily in ECE, but also in the Curie College of Computer Sciences, working towards, well, keeping our society alive or keeping our society moving. And let me talk about that. Let's get into this. So I believe that everyone here agrees that ubiquitous, universal, and secure connectivity is what drives our society. Just imagine for a moment let's for a moment remove wireless connectivity or actually any type of connectivity from you. Drop your cell phone, leave your laptop alone. You can keep them, but remove the internet from them. How would life be? Some of you may find it, well, very exciting. No more notifications, peace is back, and every life is beautiful. Some others would probably be freaking out, saying, oh my God, I don't even know how to get to my regular store where I go. I always have the GPS next to me, right? So remove all those. Well, the reality is that life would be very different. And I think that even if we look just back 5, 10, 15 years, right, we can see how much the internet and wireless connectivity has changed how we live. So let's do an exercise. How do we think that life will be 5 years from now, 10 years from now, 15 years from now? It's probably going to be very different. And well, we believe that part of that will continue to be led by the innovation when it comes to communications and networking. So in this context, what is the Intelligent Networked Systems Institute doing? Well, as I said, this is a collection of students and faculty working together on what? First of all, research. And that's why we're here today, to talk about the research that a large chunk of the Department of Electrical and Computer Engineering is doing. And in these regards, what we're doing is, our goal is to be a leading global institution for both research and development when it comes to intelligent networks. Now, we do that not just by, making new discoveries, but in the process of creating those new discoveries, we are training the next generation of researchers and professionals that will have the necessary interdisciplinary and hands-on skills to lead the community, right? So we don't just make workers, we make leaders. We don't do this just locally. We don't just write papers and, send you to local workshops. We actually try to influence the global discussion on connectivity. And I'll show you later how we do that. We do that by actually being part of the major alliances, both in the US and globally, that direct or define how the future of the society, the hyper-connected society, is going to be. And yes, we promote a lot the generation of intellectual property and then their commercialization. So we'll talk a little bit about some companies that can come out from the research that faculty and most importantly students do within the institute, within the department. Now, some of you who might been looking for Northeastern for a while may say, I have never heard this new name of Institute for Intelligent Networked Systems, but I still see many mentions for a WIOT, Wireless Internet of Things. Well, that's the old name of our institute. So literally till December, our name was Institute for the Wireless Internet of Things, or WIOT. Today, or since January, our name is the Institute for Intelligent Network Systems. And this is to reflect what has really been evolving, right? We've moved from wireless sensor networks and IoT applications to actually intelligence in the network. And as we will discuss later, AI and networking go very close together. On the one hand, through AI, we can design better networks, we can operate networks in real time, faster towards the optimal performance. But at the same time, thanks to networks, we can actually connect users to their AI infrastructure, to the models. Thanks to networks, we can collect a lot of data for those inference engines. So one needs the other and vice versa. Now, just one thing that I wanted to say, this is also new. So we changed the name and we expanded globally. So we are an institute that has both a large presence here in Boston, but also a large presence in London. Actually, we hired 2 extraordinary faculty in London last year. They already have more than 24 PhD students working with them. And that's an interesting opportunity because on the one hand, so if you're an undergraduate student, you can actually spend your first year in London, and now we're working on being able to spend even part of your second year in London. If you're a graduate student, you could, spend most of the time in Boston, but then agree with the faculty there and have one period, maybe 1 semester, 2 semesters, co-supervised by them in London. Or it gets even more exciting. If for whatever reason your visa doesn't go through, well, there is always an option, which is like, well, you can join Northeastern fully, legally, but actually be in the London campus in the UK. And once your paperwork resolved, you can move to here, or maybe no, maybe you just love the London campus so much. So that's an option. So we are international for many reasons, for diversity of research, for diversity of funding, right? Through London, we can compete for European funding. In the US, we mostly compete for US-based funding, but also for logistics, right? Visas are an issue, we understand, and we try to address that. Now, this institute as a whole was established back in 2019 with the old name and the new name. We have been able to secure over 130 millions. And you will say, and what are those for? Well, those are mostly to pay students to conduct research. So today in the institute, we have more than 200 members, 25 faculty, 36 researchers. That means people that already have a PhD. So you will see that we have many students who come for undergraduate, stay for their masters, then decide to stay for a PhD. And sometimes when they graduate, they're like, we don't want to move. So they actually stay as postdocs, and there is a career path for that, right? There is research, there is research scientists, principal research scientists, research faculty. There are many opportunities. But look at the number, 106 PhD students. All these are people who today are sitting in our facilities, conducting state-of-the-art research, and what's more importantly, fully supported by the Institute. Now, 26 master students. So yes, we do have some support for master students. However, our priority is PhD students because that's a long-term commitment, and projects are usually 3 years. So you don't want a student that comes for one semester or a year and disappears. But okay, there are opportunities too, and even undergraduate students. And I don't want you to think that, okay, research means that we need money. It depends, right? For example, when we talk to undergraduate students, they can actually get elective courses compensated for research. If you're a master's student, you can actually get your master thesis working with us and have to take 2 less courses. So there are opportunities. It's not about money. In fact, when you work with a faculty, when you work on research, you should not be driven by what much do they pay me. Actually, that's standardized across Northeastern. But it's what do you get out of the advisor? What do you get out of the group? And those is the time, the knowledge, the skills that then will allow you to find that job that you want. We do all this not just as a closed academic group, but we do that with industry and companies that are externally, but also companies that we have created. And here, just a quick display of the companies that today work with us. I would like to emphasize one thing. These are not companies that we pay for. These are companies that pay us to work with, right? That's part of that money that I'm showing you. So many times when we start working on a topic, or many times when we create a new program, and for example, some of you may have heard about the Masters in Internet of Things or the Masters in Wireless and Network Engineering. These are programs that we created not because we're bored, but because our industry partner says, Josep, we love your PhD students and we want to hire more of them. But, for many jobs, first of all, we cannot just wait for, 10 a year. We need many more. And more importantly, for many jobs, you don't really need a PhD. So masters would be great. So that's what we did, create 2 master programs that would satisfy the needs of these companies, and keep an eye on those master's programs because we're actually revamping them to make sure we capture what we're hearing from our industry partners. I did mention, however, that we also create companies, and all these are companies led by faculty, but more importantly, graduating students in the area of wireless and communication networks. And Northeastern is extremely supportive. So if you have a good idea, the first thing is protect it. Usually file an invention disclosure, then work on whether patenting it or not. Many times, yes, that's a solution, patenting it. But then connect with the proper accelerators and technology innovation engines that, as you know, in the Boston area are many, London are many. If you go in any of the other Northeastern campus, like Oakland in California, right, there are many opportunities for that. What else do we do? Well, we are not just part, again, of an academic group. We are present in the major alliances. For example, today we'll talk a lot about wireless communications, and many people think that wireless communications are designed by, I don't know, Qualcomm or Apple or maybe Huawei, depending on the country where you are. You could not be more wrong. Actually, what defines what the next generation of wireless system needs to be is actually discussed at the highest level, and that's the International Telecommunications Union, the ITU, particularly the Radio Communications Division, so ITU-R. The ITU, think of it as an alliance across 150 countries, and when the ITU approves a recommendation, this becomes an international treaty. So now let me tell you that within the US, despite being such an intense academic ecosystem, there are only 10 universities that are members of the ITU, and Northeastern is one of them, right? So we are actually very actively not just trying to solve from the bottom with companies what needs to be done, we're solving from the top by defining the directions that those companies need to follow, that those different alliances need to follow. That's just one example, right? We're members of the ORAN Alliance. We're a founding member of the AI-RAN Alliance. RAN stands for Radio Access Network. And we'll talk about this as we get on to the actual research, but a few others, right? That's one of the things that I would like to emphasize. So when you are here, right, you're taking courses with us, that's great. You're doing research with us, that's great. You're listening what companies want to need, but you're also listening from the leaders in these alliances of actually what do we think that needs to be doing. I think that's exciting. And then, okay, we talk a lot about the industry, but let's be real, right? Most of our funding comes from federal agencies. And yes, despite what the news says, there is plenty of funding, at least for engineering, in this country, from the National Science Foundation, from the Department of Defense, or well, Department of War these days, under different names, but also many others, as you can see. So with that, let's talk a little bit about research. I believe that all of you have a 6G, a 5G phone, maybe a 5G phone, and you're thinking of getting your 4G phone. You're planning to get your 5G phone. Now, as you can imagine, well, as probably you know, 5G was approved in 2018. This is 8 years ago. Now, how do the cellular generations work, right? So the idea here is that more or less every 10 years, you have a major upgrade in the system. What does the system mean? Well, you say, oh, I change my phone every other year. Yes, you change your phone. And yes, maybe it has a better screen, maybe it has a better camera, but fundamentally, the wireless connectivity piece of your phone does not drastically change every other years. There are some updates, right? But if you think of the big G, G stands for generation. So the big G's only change every 10 years. First G was analog telephony. Second G was digital audio and SMS came in. 3G was the beginning of having webs, I mean, data, email and some web connectivity on your cell phone. 4G was when finally everything took off with the apps and more data. 5G has been data on steroids and everyone streaming and up and down and this and that. And as you can imagine, if this was approved in 2018, it means that for a while, especially universities, which are the innovation engines of any sector, are already working or have been working for long on 6G. And what does 6G mean? Well, this is our vision for 6G or our roadmap. First of all, to enable 6G, we will need probably more bandwidth. And where do we get new bandwidth? Well, we'll talk that in a few slides, but bottom line, we need to look for additional resources in the electromagnetic spectrum, and that's what within the institute we call conquering the spectrum. Now, it's not that we just need more spectrum. We also need to better utilize the resources that we already have, knowing that in some cases we need to be backwards compatible. But more importantly, it's not about getting more and forgetting about the old. No, it's actually make everything old and new work together for a better user experience. Now, how are we going to do this, right? So we want to have networks that can operate maybe in different frequency bands, accommodate different type of applications, different type of users. Well, we want to do that through programmable networks that ideally should be open. We don't want one vendor to tell us, oh, you should buy the whole product from me. No, we actually believe on the innovation that can occur at different elements of your network. So we'll talk about that. And when you have many things that you can optimize how your cell phone behaves, you can optimize how the network behaves, you can optimize how your signals look, you can optimize how your network operates. There are so many knobs that we can adjust that at some point it becomes too much for a human. What we need is what we refer to as AI native processing and control of our networks. And the fundamental goal, well, the fundamental goal is to keep everything and everyone connecting, right? Trying to bridge the physical and the digital connectivity, which is what's happening these days, right? So try to connect everyone on the ground, in the air, in space, underwater, you pick. That's where we are. Now, what we're going to do in the next 20 minutes is to spend some time going through at least some of these blocks. Particularly, we'll spend a little bit more time on the first block, which is conquering the spectrum, because it happens to be the research that my group is doing. I didn't say it before, even if it was one of the lines in the cover page. On top of all these titles, I do direct a research lab. We call it the Ultra Broadband Nano Networking Laboratory. And this is a group that has existed for years, right? I mean, let me put it this way. Actually, probably this should come at the beginning. So I've been at Northeastern for 6 years and a half. During these 6 years and a half, we've been doing very exciting work that you'll see in the next few slides. Before that, I was at the university at Buffalo, SUNY Buffalo, where I was extremely happy. I was a tenure track faculty. I got my early tenure promotion, fine. Before that, I got my PhD from Georgia Tech. This was 2009 to 2013. Let me give you a data point. 2009 was the year that 4G was approved, right? Now, what has in common what I did as a PhD student, what I did at Buffalo as an assistant professor, and what I've been doing here at Northeastern as my career kept moving, has always had a common keyword. And that word is terahertz. You're going to see why. Terahertz, if you haven't heard it before. So you already seen these questions, right? We said, okay, connectivity is at the cornerstone of our society. But you're telling us that you want to connect more things, and not just things, of course, more people, more things everywhere, underwater, underground, on the ground, in the air, in space. We're talking about many, many, many things here. How can we accommodate all these increasing number of devices, an increasing number of applications, and a new type of traffic that these devices generate? Having many devices just sending temperature measurements, the old problem of wireless sensor networks and IoT, that's not a problem. The problem is having many devices streaming 4K video, right? That's a problem for your network. So we said the first goal of our institute is to conquer the spectrum. Okay, where do I find more electromagnetic spectrum? Let's start with the following frequency axis between 0 and 10 terahertz. If you think of every wireless service that you're utilizing today, and note that I use wireless service, I did not say wireless communications, because I think that sensing is important too, and it's also wireless, right? So you can talk about radio and TV broadcasting. I don't think anyone listens here, watches the on over-the-air channels anymore, but well, maybe the radio in the car, fine. Your cellular systems, your Wi-Fi, but also your radar, right? Or that remote control for your car or garage opener, GPS. All these services operate primarily under 6 gigahertz. If you want to be generous, taking into account the millimeter wave adoption in 5G and some other radar applications, okay, under 100 gigahertz. So if you look for more bandwidth under 100 gigahertz, you're going to have a tough time because pretty much everything has already been allocated. The spectrum has been chopped and tiny pieces given to different applications. Fine. If we only want bandwidth, we could always jump all the way to optical frequencies. And let me put it this way. When I was a student many years ago, right, when we learned about electromagnetics, we would have these professors come and teach us about microwaves and antennas and propagation. And we would always talk about low frequencies, and that's fine. Then we had these courses about people talking about optics and photonics that seemed to come from another planet. But remember, whether we're talking microwave or infrared, we're talking about electromagnetic energy. Therefore, we represent it on the same axis. So yes, if you want a lot of bandwidth, you could jump to infrared communications, you could jump to visible light communications, any optical wireless communication system. And there is many interesting research going on into that. But what my group and a large chunk of our institute has been working on for many years now, again, as a student from the beginning of my PhD, has been what happens in the middle? What's between these microwaves and millimeter wave and the optical systems? That's what we refer to as the terahertz band. And that's what we're going to be spending, let's say, the next 10 minutes. First, why do we care about these frequencies? Well, there are three reasons or three properties that are going to justify what we're going to be showing you next. First, yes, we go to these frequencies because, well, not many people use them. We expect to find a lot of bandwidth. And the more bandwidth you have, the faster you can talk, or maybe the more people that can talk at the same time. So that's good. What else do we get? Well, the higher the frequency, the smaller the wavelength. Remember, no? The product between frequency and wavelength is the speed of light. The speed of light is constant. So if you increase frequency, your wavelength goes low. Then what happens? At terahertz frequencies, your wavelength is just a few millimeters or less, like down to tens of micrometers. And what does this mean? This means that you can make very small antennas, for example, because usually your antennas just have a wavelength, or you can make, if you give me the same size for the antenna as you gave, let's say, a microwave designer, well, in the same footprint, I can place so many small elements that I can actually generate a very high gain antenna. And that's interesting. You can actually have, as you will see later, some applications that have to do with, well, either you have very small antennas that you could place anywhere, even on chips, even inside your body, or you can have still very small antennas, but that give you a lot of gain. You'll see what we enable with that. There is one more application, however, the one more property that many times as wireless engineers we forget, but it's important, which is the idea of photon energy. Remember, I just told you that we can think of the electromagnetic spectrum either as waves or like the radio wave people or as an optical system. And remember, the people in optics don't usually talk about optical waves. They talk about optical particles. What are those? They are photons, right? So at low frequency, we talk about electronics, right? And we deal with electrons and eventually we shake them and we get to have an electromagnetic wave coming out. At optical frequencies, we talk about individual photons that sure we can manipulate individually or as a group. Now, this photon energy, the energy of each individual particle, right, is proportional to its frequency. The higher the frequency, the higher the photon energy. So at optical frequencies, your particles are energetic. We can see them, we can tell them apart. That's why at optical frequencies, we talk about photonic systems. But at low frequencies, radio wave, microwaves, your photon energy is very low. So what happens? We cannot individually see photons. That's why we don't talk about photons at low frequencies. We usually talk about waves. And what's a wave? A group of photons. So remember, light particle, wave particle duality of light, that's real fine. Now, why do we care about the photon energy at terahertz frequencies? Well, at terahertz frequencies, your photon energy is not enough to break anything. We are not ionizing. We cannot split molecules apart because our photons are very energetic. No, they are not that much, but we can shake things. We can actually induce vibrations into different type of molecules. We are actually absorbed by different type of materials. And that's going to be interesting, and this will allow us to create new types of sensing. Now, what do we do with all these properties? Well, the terahertz band offers many applications, applications that have been evolving throughout the years. On the one hand, for example, when we started working on terahertz, we thought that the terahertz band was only good for very short distance, and we wanted to take advantage of the tiny size of the antennas to place them anywhere. That's why we were talking about terabits, so very fast, but nano networks or body area networks, right? Some short range. Then, with the development of better technologies, as well as a better understanding of how these signals propagate, we were able to start pushing for the distance. And we said, no, it should be more than the body. It should be a wireless access network like your Wi-Fi, or maybe even a few hundreds of meters or a few kilometers. We can talk about terahertz for wireless backhaul, like connecting the towers. Fine. Today, however, as we'll show you in a few slides, we're pushing for terahertz all the way to space. And we're going to be talking about satellite and space networks in the terahertz band. Now, usually people relate wireless to communications, but there is another key group of applications that are wireless, and that's wireless sensing. Sensing means different things to different people. We can talk, for example, about radar, knowing how far a target is. We can talk about imaging, knowing the shape of the target because we do a scanning. We can talk about the spectroscopy, knowing the molecular composition of the target because we are doing frequency scanning, right? So frequency and spatial scanning give us very interesting modalities of radar. And yes, we can do that on the ground, but we can also do that from space. Would you believe me if I told you that at this precise moment, as we're listening to this live podcast or webcast, there are already satellites orbiting the Earth that carry terahertz radios in them. Those radios are not transmitters. They are not there for communications. They are receivers. They are listeners. And they are both listening down to the atmosphere to understand the composition at the different altitudes of the atmosphere. For example, for prediction of weather as well as climate change monitoring. But also they are listening out. They are capturing the signals that come from outer space that were produced in the process of new stars being formed, new galaxies being created, new stars disappearing, all stars disappearing, right? So this has already been happening, and this is something technology that has existed for a while. Now, we are in 2026. No one talks about communications or sensing. Everyone talks about communications and sensing, or the integration of sensing and communications. And that's what is driving us today. How does an integrated sensing and communication system mean? Well, imagine, for example, you are indoors and you need to provide high-speed connectivity to different users. As we will learn in the next few slides, this means that we will have to generate beams to different users carrying a lot of data. Those beams may be blocked, so we will have to think how to get around obstacles. We'll talk about that, but we may need some helpers like intelligent reflecting surfaces. But now imagine that these exact same radios, including the one on your cell phone, not only are exchanging data, but they are collecting data from the environment as they go from the transmitter to the receiver and vice versa. Well, that's what sensing means. And for example, I can build a system just with the exact same radio, same signal, same frequencies that can tell me how many people are in the room. People are different from furniture. So yeah, how many people, maybe how many empty chairs, and not only that, what is the quality of the air that these people are breathing? That's amazing. How can we do that? Well, we can see how things look like because I'm dealing with a small wavelength. I can know what things are made of because I have enough photon energy to trigger these unique electromagnetic signatures. I can do this in the ground. I can take this all the way to space. I just told you, right, that there are satellites orbiting the Earth that are doing sensing. Well, we think those satellites, right, could also communicate at terahertz frequencies. So we could create links between satellites. Today, the major push has been for the use of optical technology. We'll talk about that later, but actually terahertz brings some interesting properties to the table. We can try those satellites to communicate with the ground utilizing the same frequencies, maybe individually or as a team. But again, we can do all these things while with the same satellites, with the same radios, we are collecting data, both from the atmosphere and from space. And this is very exciting because these days, I'm sure you follow the news about, there are more and more satellites in orbit. Like it started several years ago with Starlink launching satellites by the hundreds every month. Now we have thousands of them, different competitors trying to do the same. Now you may have heard about the latest, which is like, no, let's move data centers all the way to space. Why? Because if you're in space, you can actually track the sun and have infinite solar power. And if you're in space, you are by default cool, like very cold, like a few Kelvin, right? Because that's how cold space is. And don't get me wrong, that fundamentally makes sense. There are some challenges, engineering challenges, and we love engineering challenges because we are engineers, and engineers solve problems. So, hey, life without a problem is not the life of an engineer. So there are many things going to space, and some people are not happy. The people who are studying space, they say, look, you just keep throwing trash to space. Now, what we're saying is that, you know what? Let's make some of that trash useful. Not that I'm calling satellite communications networks trash, but let's make them useful to collect data. Fine. Now, these are applications, and they're interesting if you ask me. Then you'll say, Josep, so why are these not out? Well, these are not out, despite we've been working on them since 2009, because there have been many challenges. First, if you look for a terahertz radio, good luck, right? You cannot just buy a terahertz radio on Amazon or Temu or Alibaba. Those they don't exist, right? There are some. Today, at least, there are some very few, but at least they exist, vendors that can sell you terahertz radios. So I'll show you in one slide what we have been doing as a group in order to advance the technology for terahertz systems. Then we need to understand how terahertz signals propagate. If you have a radio, but the signal gets attenuated very quickly, what's the point? So we'll share with you what type of research we have been doing related to propagation and channel modeling. Now, once you know what the hardware can do, what the channel will do, it's when we can start working on designing those signals and learning how to process those signals. So communications and signal processing. And we'll show you in one slide an example of what we're doing with signals today. And there is more, right? We want to build networks, not just one point-to-point link, and we want to make sure that our research has an impact. So we need to make sure that the research is legal, right? So we need to satisfy spectrum policy. But how is a spectrum policy of a frequency band that no one cared? Well, it's uncertain. So today we can talk about spectrum policy in the terahertz band. For years, even when we started, what policy? No one cared, right? And more only that, we also need to then agree on how to use these bands. So we need a standardization. We'll talk along those in the next few slides. So terahertz technology. I told you that you cannot buy a terahertz radio, but let's do an exercise. What do you need to build a terahertz radio? Well, you need three things. First, you need front ends. What's a front end? The front end means the analog part of your radio. The devices like the oscillator, the signal mixer, the amplifiers, the filters that can work at these very high frequencies and ideally with a lot of bandwidth. The good news is that, well, today, if you stop by our lab here in the Boston campus, we can show you many solutions. Solutions that we have co-developed, for example, with Virginia Diodes or NASA JPL, the Jet Propulsion Laboratory in Pasadena, California, that have world record transmit power. World record transmit power at these frequencies means hundreds of milliwatts, so don't get too excited, but that's interesting. Those are both electronic systems. We could also show you some of the patterns that we have, including some of the very early demos of a different way to generate signals. We call it the plasmonic approach to signal generation that builds on new materials like graphene, as well as other two-dimensional nanomaterials. What else do we need to build our radio? And that's actually a snapshot of our graphene plasmonic device. What else do we need? Well, we need antennas, right? Again, how do you build a wireless system without antennas? That's why electromagnetics are key to any ECE department, or actually to any wireless system. So we need antennas. I told you that they can be very small, on cheap, or if you let me use the same real estate on your low frequency radio, I can get a lot of gain. So yes, I need antennas at the transmitter, at the receiver, along the channel. Not only that, we are in the middle. People at low frequencies talk about antennas, but people at optical frequencies, if you look at a laser, there is no antenna. And please don't look at a laser when pointing to your eye. But if you look at a laser, you don't see an antenna. What you see is a lens. So at terahertz frequencies, sometimes we have antennas, sometimes we add lenses on top of the antenna, or sometimes we have the discretized version of a lens, which can be a meta surface. So we have many antennas that we have designed and that we have built and we can show you in the lab that have different functionalities. And yes, some of them you can have today, some of them we're really working hard. We're generating tons of intellectual property that then we can license even to our own company or to an external company. For example, when it comes to making arrays out of this. But there is one more block to build your terahertz radio. We need the ability to interface these analog things, the analog front ends, the antennas are analog too, right? With your compute power, your cell phone, your computer, your data server. Those are all digital, right? So we need a very high speed digital to analog and analog to digital interface. And if you come to many of our labs, right, you will see, for example, Keysight equipment, right? Signal generators, digital storage, oscilloscopes, and these are all great. The problem of this is that these are great in a lab, but first of all, these two pictures you're seeing here, it's more than $1 million in equipment. And I still have two kidneys and I don't want to have to sell one. So yeah, we're keeping it like that. What's interesting is that this type of equipment is what you get exposed to, not just in our research lab, but if you come to our ECE department and take the right courses, we have, like, for example, there is a wireless comms lab that I created with Professor Elena Bernal-Moore. And in that lab, we have 8 workstations, each one equipped with one of each, one signal generator, one digital scope, one portable vector analyzer, a bunch of antennas, a bunch of different additional components that we use not just to perform testing of the equipment, but to program the signal processing techniques, right? So you get exposed to all of that also when you take your courses. So research and education go really together. But again, if I want to go beyond this learning equipment or lab equipment, we need to go to platforms that are, much more smaller. And for example, we have been working and patenting new ways to highly parallelize digital signal processing so I can run gigabits per second of data and more, even if I'm running on an FPGA that is clocked at a few hundreds of megahertz. Hundreds of megahertz system operating gigasample per second data converters. That's the type of work that we do when it comes to hardware for terahertz systems. And again, I think it captures quite well the different elements that you get to see in ECE. You get to see materials, you get to see semiconductors, you get to see electronics, photonics, plasmonics, electromagnetics, and actual IC digital hardware. That's what we are. Now, for example, today, if you stop by the lab, we can show you our Terranova testbed, which is the integration of all the terahertz toys that we are consistently using for testing of many things. For example, we cover the bottom box and we say the bottom box is the hardware. What else? Well, how well terahertz signals propagate? Well, in our department, we do a lot of work when it comes to studying the wireless channel. And for example, when it comes to my group, we've taken our terahertz toys and placed them indoors. We've measured how terahertz signals propagate within classrooms, within conferences rooms, within offices. We've done all those things. But there is a beautiful thing of being in Boston, which is we have 4 seasons. Yeah, we have a very nice summer. We have a beautiful fall with all the leaves falling. So how does foliage impact terahertz signals? Well, that's something we can study. We have a winter with the snow, yes. So I agree. I mean, the first snow is always nice. The last snow in March is like, come on, please. But we do have snow. And yes, we have beautiful green and rainy springs. So many people ask, Josep, terahertz signals indoors fine, but outdoors, what happens with the bad weather? Well, these are the type of things that we can do, right? We can build a channel sounder that can characterize the terahertz channel over very large bandwidth in the presence of good days, rainy days, snowy days. So that's other type of research that we also do. Now, I told you, with the hardware and with the understanding of the channel, we need to design the signals. And for example, right, if you come to our department and you will be educated in all aspects of signal processing, analog and digital signal processing. Within digital signal processing, digital communications, right? And in our system, we've tested every possible modulation scheme that you can think of. Single carrier, multi-carrier, OFDM, DFT spread OFDM, OTFS, spread spectrum, all of them. And by the way, when I say we teach you, I say we teach you in theory, and then you go in the lab and do it. And I need you to have those skills because then you come to my lab and test that. The difference is that instead of having a 100 megahertz channel, you have a 20 gigahertz channel, right? So there are more challenges there. So we've done a lot when it comes to processing signals in time and frequency. But today, if you ask me, what's the most exciting part these days happening in the lab? There are two. The first one is what I show in this slide, which is the process of signals not in time and frequency or in addition to time and frequency, also in space. So how can I control my radiation to go to different ways? Some of you might be familiar with millimeter wave systems. In millimeter wave systems, you have directional antennas and you can point your radiation in different ways. Fine. What's interesting is that at terahertz frequencies, there are some properties that kick in, including the fact that in many cases, you're going to be within the radiative near field of your antenna. And when you are within the radiative near field of your antenna or the Fresnel zone, you can send not just beams that go in a way, you can send beams that have very unique properties. I can send beams that focus at a point, and that's great if I know where to focus. I can send beams that focus along the near field, and not only that, even if those beams are blocked, the problem that I mentioned before, we can recover them. And for example, here is an experiment that we showed a couple of years ago on how we can generate a new type of beam. It's called a bezel beam. I mean, let's be honest, it's not a new type of beam. It's a beam that at optical frequencies has been used for sensing. Now here we're using it for communications, which is a beam that can recover from blockage. Let me show you a result. When I have my antenna and I don't do anything to it, and I send a signal and I place a metallic pipe in front of it, I cannot recover from the obstacle and I don't recover my data. I have red transmitted points, I recover a blue blurb. Instead, when I'm at this lens on top of my antenna, I have a bezel beam, and this bezel beam can recover from an obstacle. This is just one example of what we're doing these days with signals. We've done other things, like, for example, we set a few world records. It was in 2018 that we established the first multi-kilometer long sub-terahertz link carrying lots of data. We did this in collaboration with the Air Force and utilizing some custom designs from NASA. So yes, all the red agents were involved here. And we did this in the middle of New York State. So 2 hills and a valley in between. We did that with innovation at the hardware level, at the signal processing level, at the electromagnetic level, and all together. So please keep hearing this, right? You want to become an expert in something when you do research. And sometimes that expertise comes precisely at the interface between disciplines. That's what the EC department is good at. That's what the College of Engineering is really good at. Now, so if in 2018 we were already doing multi-kilometers link, what am I doing today? Well, today we're pushing for the next frontier. And I'm very happy to report that with the support of the National Science Foundation, the Air Force Research Lab, as well as NASA, we're building, launching, and operating what's going to be the world's first satellite with terahertz communication capability. We said that there are satellites with terahertz sensors. We're building the first satellite with terahertz communication capability. NSF is helping convert one of our radios into something small enough that will fit into a CubeSat. The Air Force is actually guiding us onto the design of the CubeSat and the whole mission planning, and NASA has agreed to pay for the launch. We have our flight selection review at the end of this year, hoping for the best. If so, next year, this is the go, no go decision. If this doesn't work, well, if this works, next year we're launching, which is extremely exciting. And let me say one thing. Sometimes when you look at the offerings of Northeastern, you'll see many things. But one of the things that you may miss is that we don't really have an aerospace program, but not to worry, because we do have the building blocks of an aerospace program, right? We have electrical and computer engineering, and we have mechanical and industrial engineering. And the result of that is that we do have an extremely strong student club, the Aerospace NU. And not only that, it became so big that it was difficult to manage. So the satellite division of the Aerospace Club has become a new club, the Northeastern Satellite Lab, NSL, for which I happen to be also the faculty mentor, just because I'm not busy, I guess. So faculty advisor for the new Northeastern Satellite Lab. And this is just the mission that I'm showing here. It's one of them. Actually, we already completed a smaller mission, but nonetheless very exciting, which is we contributed a 1U to a small constellation that will flight information, and the launch is next month. So yes, we're at a point that Northeastern is launching satellites. We're at a point that you can contribute to that, and you can contribute by enabling how to launch those satellites, or you can contribute by saying, I really would like to test this technology in space. Well, we have the infrastructure to help you do that. Again, I know that this is common to some universities. For Northeastern, it's now an option too. Now, you will say, Josep, in your roadmap, you showed us many boxes, and here you spend a lot of time on the first box. I know, I'm biased, right? It's my research area, and as you can tell, there are already many things to say. I just wanted to briefly tell you a couple more things about other boxes. So I wanted to say, look, when I talk about what the Institute does, I would say conquering the spectrum is one of the main things, but the other has been to advocate for the adoption of open radio access networks. What does it mean? Well, to give you an idea, I think that you all know how to set up a Wi-Fi network, right? You pay someone to bring you internet to your home, and then you go and get a Wi-Fi, an access point, connect it there, and you have Wi-Fi. Fine. Do you know how to build a cellular network? Like, for example, if you were to come in the US, you would have to buy a cell phone from either AT&T, T-Mobile, Verizon, or a few virtual operators, which are operators that work on the networks of AT&T, T-Mobile, Verizon. But can I go and create a private 5G network? And the answer is yes and no. Till very recently, the only way for you to create a cellular network was to go and talk either to Ericsson in Sweden, Nokia in Finland, Samsung in Korea, or Huawei in ZTE in China. Note that I did not mention any US-based company. And why? Well, there was one, Motorola, but after the lack of success in 3G, that disappeared, fine. But the reality is that if you want to create a cellular network, you need to just go and work with one of those vendors, and they will send you what we know as a closed solution, a black box. Instead, there has been now for over 10 years a major push for the adoption of an open radio access network, a network in which the different building blocks from your network are known, it's not a black box, and might come from different vendors. The only thing that you need to ensure is that their interfaces are standardized. And what does this mean? Well, that doesn't mean that now you can work with the best antenna designers for the tower antennas. You can work with the best signal processing company for some of the signal processing. You can work with the best networking company for the networking aspects of it. And then you can just put all of them together. This brings competitiveness. This brings the ability of having really the best solution for every single block. And of course, we like that because at Northeastern, we are developing solutions for each one of these potential building blocks. Now it's okay. Now, in all this context, what's important is, like we said, programmable networks. Programmable networks means that we can touch upon different elements, right? So we can program the radio aspects, we can program the signal processing aspects, we can program the network processing aspects. And what's important, if you can program, right, if you can change, right, it means that you can also add intelligence to all of them. And that's why usually we went from O-RAN, having radio access networks that are open, to AI-RAN, having radio access networks that are intelligent, right? And the AI-RAN Alliance, which It's mostly industry with two founding academic partners, that being Northeastern University and the University of Tokyo, was created a couple of years ago. And we're talking about artificial intelligence for the networks and running the networks, which is important. And this artificial intelligence enters this open run model in many ways, right? We're talking about networks that should be able to self-generate themselves. We're talking about networks that should be as simple as you buying the components, connecting, clicking, pressing a button, and let it start operate, understand its surrounding, understand which frequencies it should work out, where the users are, all of this, extracting information from the networks. And of course, in 2026, it's all about agentic AI. So having agents run the network, program the network, react to a problem in the network. Don't get me wrong, we are not removing the human from the network. The human is still first a user, but also the initial designer of the network. But we're making the life of network operators much simpler, and for those who are good, have much faster hands. I'm going to just say one thing, please, hopefully no one gets sad. But these days, I refer to an AI agent like Claude, that it's what we use here at Northeastern, as perhaps my fastest student. But first of all, it's still a student, it's still learning, and I still need to provide very careful guidance, but it is very fast. So what's helping me? It's helping my group, and not just me, help my group be able to perform our research faster. Well, anything can be done faster if you know how to use the proper AI tools. And of course, we also teach you here when you come to Northeastern. We have many other toys that we use, like Colosseum, which is the world's largest radio frequency emulator. Think of it as a data center, but that instead of solving very complicated problems, is actually emulating networks. Like, you can load the topology of your favorite city in the wall, you can place the base stations, you can let the users go wild, you can define the protocols that these users should be following, either old or something new that you have just conceived, and then see how well the networks operate before you deploy it in place. And we have plenty of networks that we use in our research, also at lower frequencies within our buildings, at this moment, mostly in EXP, as well as in our Burlington campus. With this, I did want to have some time for questions. So I'll stop, take a breath, but I wanted to say we are excited with what we do. We think that, if anything, intelligent networks are going to play even a bigger role in our society. Intelligence, right? What is that? Computing. For that, what do you need? Computers. Do you need computer engineering? You need electrical engineering to build those transistors in that component, right? And you need materials, right? You need networks, you need communication, signal processing, electromagnetics, antennas. Of course, all this needs power, right? So ECE is the department that it's really at the core of everything that's running our society today. And we hope that you join us. We hope that actually you share the excitement. With that, I know, right, Gretchen, you have some slides. Sorry, I'll let you go through that. I just talked too much.
No, no worries. It's always so exciting to get to hear it. I know Joseph offered to answer any questions, so if y'all want to put those in the chat, if not, his email was there, and I'm sure you can follow up. I'm just going to
Yeah.
go through a couple of quick admission slides. You can go to the next one. Now that we've heard all this great information about what is going on at Northeastern, just want to talk a little bit for anyone who's maybe at the beginning of the application process, very excited about getting something in, not sure where to start. It is a great time to be joining the College of Engineering at Northeastern University. For one thing, we currently have no application fee for all of our MS programs. For anyone who is interested in completing a PhD application, we also are currently waiving that fee to make it more accessible to everyone. You will see that highlighted Apply COE 2026 code on the screen there. You'll be able to enter that in on your PhD application. I would like to point out that it is case sensitive, and you cannot retroactively apply the application code. So you need to put it in when you're completing it, when it comes to the application fee waiver page of the application itself. If you're doing an MS application, you will be able to move right through that, and it will not charge you anything. In addition, the materials needed for the application is going to include 2 letters of recommendation, your unofficial transcripts, a statement of purpose, and a resume. If you are an international student, we do require an English proficiency exam. We accept all 3 of the ones listed below. Those minimum requirements for test scores are going to be listed on our COE website, which I will link at the end of this. And then you'll see that GRE at the bottom currently has a line through it because we are GRE optional. We find that the rest of the application materials give us a really full sense of what applicants bring to the table, and we are not requiring the GRE for that reason. Next slide, please. Just a little bit of an overview on the application deadlines. Again, these will be on our COE graduate admissions website. If you are looking at fall entry, you can see all of the dates so far. Obviously, all of the early action deadlines have passed for fall entry, but we do have our final deadlines open for PhD and master's students, depending on your international or domestic status. To be able to start this fall 2026. If you were thinking that's too soon, you're looking more spring 2027, on the right-hand side of that screen, you will see plenty of time to still get those in for spring. November and December are going to be the final deadlines for that. So again, you can submit your application at the link below. Depending on your situation, those are the dates you want to make sure you're paying attention to. Next slide. Want to highlight really quick just some scholarship opportunities that we have for some MS programs for fall 2026 and spring 2027, those current open applications. A lot of different programs being offered. A couple of those are under the ECE umbrella on our West Coast and obviously on the East Coast as well. I won't go through all of the programs specifically because, again, you can find this online, and I know we're a little pressed on time right now. But again, automatic 25% scholarship for any of the programs listed there for the next two enrollment terms. Next slide. I think we're pretty close to the end here. One more pitch that we have for the admissions team is going to be for our Engineering Wonder Week. If you liked what you saw Josep present on today, we're going to have additional sessions in our Wonder Week for all of our departments. If you're maybe between a couple, you're not quite sure where your interests land, real quick, where you will be able to meet professors and hear a little bit about what is going on in the departments, as well as get a little bit more of an admissions focused overview. So use that QR code if you are interested in any of those sessions in April. Next slide. And this is going to bring us to the end. Again, these are all the ways to keep in touch with us, especially if you want to reach those graduate admissions websites. College of Engineering website listed there, application, the admissions office, email if you have any questions, if you already have an application in about the status of your application, any mission materials, things like that, all the ways to get a hold of us. I recommend just a quick screen grab of this page right here. I think you can also use that QR code if that's a little easier for everybody. And then I think that's going to bring us to our last slide. Thank you all so much for spending your morning with us. I know we only have about a minute. I think there's only one question I'm seeing in the Q&A, maybe a couple coming in. Key qualities do you look for in a PhD student, Josep?
That's a very good question. And what I would like to say is the following. So what's a good PhD student? It's not necessarily someone who already knows everything. It's someone who is able to learn everything, right? Think in the following way. As a student, right, you've been learning what someone taught you for many years. A PhD student should be able to learn, but more importantly, should be able to create knowledge. My recommendation, if at all possible, right? Many of you probably go first into a master's program. Try to get exposed to research during that. If you cannot do a master thesis, which is a 2-semester commitment, at least do a research project and show two things to the mentor, right? So on the one hand, get good grades on your program, right? Many times I have students coming and say, oh, I want to work with you. Well, first survive in Boston for 1 semester, right? Let's see how that goes. And then, sure, let's get together, identify a problem, and let's see if this problem you can solve within 1 semester. And again, I'll calibrate, we'll see what happens. But that's the idea, right? It's not a student who already knows everything, it's a student who can learn. And for that, we need to work together. Now I see the other question. So is there funding available for master students? Yes and no. So as I said, usually federal funds, the priority is for PhD students because it's a long-term commitment. That's the only reason, don't get me wrong. There are some opportunities every now and then. So there are shorter projects that could suffice with a master student. Now, it's also relevant to know that if you come as a master student during your first year, you cannot get support as a TA, for example, because you need to spend at least 2 semesters here to then calibrate yourself and be able to be a TA. But from your third semester, many of our master students end up being course supports, so graders, course assistants, not teaching assistants, but course assistants. So there are some options for that.
I will add on to that as well that anytime you put in a master's application for the College of Engineering, you are automatically considered for our Dean Scholarship. There's a number of automatic application-based scholarships that will get applied if you meet the criteria for those. Some of them are specifically for international students from certain markets. Some of them are geared at domestic students. A fair number of our domestic students all receive some type of funding in some way. And again, that 25% automatic campus scholarship that I briefly went over for certain programs on West Coast and East Coast programs, a few of them under the ECE umbrella are available if you choose to study in Oakland, for example. All of those are going to be on the COE graduate admissions website as well, along with any other resources we have for external funding. I will type the code again for the PhD application. It is again that capital A apply COE, all caps COE 2026, for anyone looking to put that in. We are a little bit over, and I think we've moved through at least that first initial group of questions in the Q&A. So just want to take a minute and say thank you, Josep, for a wonderful presentation. It's so exciting to see what's going on in Boston and beyond within the department. And we're just so grateful for the work and the opportunities that you're bringing to the campus.
No,
And then
thank
thank
you
you
for
all.
giving me the opportunity to share this.
Absolutely. And then thank you all for joining us. Again, we have a couple of these different research webinars coming up. If you're interested in what more departments and faculty members are doing, you can find all of that on our COE events page or by attending our Wonder Week as well. So thank you all so much. Really appreciate you spending your morning with us or your evening, wherever you're coming in from. And we hope to see an application from you soon.
Excellent. Okay, well, talk to you soon,
Awesome.
Gretchen.
Sounds
I need
good.
to
Thank
run
you,
to the
Joseph.
next one. Thank you.
Yes, run to the next. I'm going to end this
Bye.
recording and we'll go from there.
Bye.